Hello, my name is Vitas, and today I will be giving the second lecture on the alchemical free energy calculations, and I will concentrate on the applications of these calculations on proteins, nucleic acids, and ligands. So we will be dealing with mutating amino acids in proteins, nucleotides in DNA, and we will apply arbitrary modifications to organic molecules, so drug-like compounds, for example. And for all of these applications, I will be referring to the package which we termed PMX. It's an in-house developed package in our group, and it allows performing all of these alchemical modifications for you. So let's start our presentation with the amino acid mutations. We will deal with the 20 canonical amino acids here, and we will deal with alchemical perturbations to complete thermodynamic cycles like this one that I'm showing here. This cycle shows how to calculate the free energy of protein folding, but not the absolute, but the relative free energy of protein folding upon an amino acid mutation. So how much this folding free energy would be different if the blue amino acid, for example, here tryptophan, would be replaced with the phenylalanine, in this case with the red amino acid in this cycle. So we could naively think we could calculate this by going in the vertical line, so performing the actual folding simulation, so one folding simulation and another one for the mutant, and taking the difference of these two free potentially well converged free energy estimates. But we can do it alchemically by going in the horizontal directions and obtaining exactly the same delta G. Of course, such a simulation is not a standard one anymore. If we need to actually mutate an amino acid on the fly, right, it requires a special treatment of our structures and topologies that we provide to the molecular dynamics simulation engine. We are using GROMACS in this case. And how to tell GROMACS that we need an alchemically modified amino acid? Well, that's exactly what PMX allows us to do. So how it works under the hood, it actually creates a hybrid amino acid. Here I'm using an example, valine to phenylalanine. Let's say we want to mutate valine to phenylalanine. We need to represent this amino acid. It's both states, and also its hybrid state, right? So in state A, it has to be valine. In state B, it has to be phenylalanine, and in between, it has to be some linear interpolation between the two of them. So this all is achieved by having PMX make its magic under the hood and provide you with a hybrid structure and topology which you can plug into the simulation engine. So how PMX works, just very briefly, it is a set of Python scripts and modules which takes a structure, and firstly it mutates mutate.py, for example, it mutates the amino acid and creates a hybrid structure. Then PDB2GMX, that's a GROMACS tool which creates a topology, and then we add the B state, so we just adjusted the topology to get a hybrid topology. All of this workflow seems quite complex, but it also can be achieved via PMX web server, so you can see that exactly the same workflow then is just hidden in just in a few clicks, mouse clicks in this web server. And one more thing, just before going into the applications, I would like to tell a little bit about the non-equilibrium free energy calculation protocol, which we'll be using in all of these applications that I will show later. So it is a powerful approach, not so frequently used as the equilibrium approach. However, it has its own advantages, and how it proceeds. It's slightly different from the classical stratification approach, which FEP approach, for example, uses. In this case, we are simulating one state of the protein, so wild type state in equilibrium, state A. We also do the same. We simulate in equilibrium, just run a molecular dynamics simulation in state B. We acquire the two equilibrium trajectories extract the snapshots from them, and start very rapid non-equilibrium transitions. Those transitions are on the order of hundreds of picoseconds. So very quickly we introduce a mutation, so from wild type to mutant, and also going backwards from mutant to wild type. During each of these transitions, we record the work required to perform this transition, and plot them in a histogram way, as it's visualized there in the small histograms on the slide. Once we do this, we can also use Crookes fluctuation theorem and extract the free energy difference between those two states. Right, so we now have all the technical background that is needed to go into the applications, and let's have a look at the protein thermostability. So we wanted to know what is the free energy difference upon amino acid mutation in protein folding. We looked at the Barnase, and it's a very good test system because it has been studied experimentally very thoroughly. Here we collected 119 mutations at 55 positions. You see that almost whole protein here is covered, so we can mutate almost every residue in it, and we can compare against the experimental measurements, and this gives us a very interesting thermodynamic comparison of the force fields. We can check which force fields perform better and which worse in terms of agreement to the experiment. Right here I'm showing averaged unsigned error. AUE is averaged unsigned error from the experiment when averaging all the results for all of these 119 mutations, and we can see that all the force fields perform quite well. The differences between the force fields is about 1 to 2 kilojoules per mole, and the newer force fields, they are Charm 36 and Amber, with the modifications, they perform significantly better than, let's say, an older force field. In this case, we used an older version of the OPLS force field. So we can start really looking at the thermodynamic comparison of the force fields, and we can also look into an interesting avenue, how to combine the results in the best way. So here I will not go into much detail, but we can start building now consensus results of the force fields. Either we can use some machine learning technique like partial least squares technique to build one single best answer, let's say by combining the results from the two force fields or from 5 of them. And actually we noticed that even combining the results from only 2 force fields, so our best Amber version and Charm version, it once combined we would get a better answer than a better agreement with experiment than when using any of the single force fields. Similar result comes out also for a different protein. We also probed, it's not only working with that Barnase, but also here staphylococcal nuclease. It also gives a very accurate free energy differences below 1 kilocalorie per mole. This is like a golden limit, which usually people strive to reach in accuracy of these calculations. So we are well below that limit, and also again the consensus approach works better than a single force field taken separately. We also can use these amino acid mutations to probe not only protein thermostability, but for example also look at the drug resistance. So in a number of applications we have looked now at how much the drug resistance would be induced by a protein mutation. Here is an example of this HIV protease. So protease itself is a protein which is necessary for HIV maturation, and it is one of the main targets for all of the anti-HIV drugs. The virus, however, once it evolves, it becomes resistant to the anti-HIV drugs by means of mutations. Here are several mutations that I'm showing in blue. So they are known from sequencing of the genomes of viruses of the patients who have been treated with anti-HIV drugs, that those positions are usually mutated, and then again the virus escapes the drugs, the effects of the drugs. So how could we probe for the effect of a mutation on a drug by means of the free energy calculations? So here we would construct a slightly different thermodynamic cycle where we would have a mutation in the HAV in its apo form with respect to a mutation in the HAV in its holo form where the drug is bound. But all the other machinery can be is identical to the one that I described previously. All the simulation technique and the non-equilibrium free energy calculations. Now, what we looked at was many of those mutations. So here I marked a few of them, and we looked at a number of known HAV protease inhibitors. They are actual drugs that are on the market, and we were able to recover a very good agreement with the experiment just by performing exactly the same calculations that I outlined before, and we are able to recover a very good correlation, as you can see, for 6 ligands, so 6 known HAV drugs, although there is a slight offset. But in this case, we did not employ our consensus force field. We know that would likely improve the results a little bit, but we are already quite happy with such a good agreement with the experiment. In the next step, then we dug even deeper. We looked at even more mutations. However, in this case, we looked at those mutations that are further from the actual binding site of the ligand. So this would be particularly challenging because these mutations, when they occur and have an effect on the ligand binding, they actually do not directly interact with the ligand, so they make some indirect changes in the protein structure, or maybe it's a dynamic allosteric network. So first of all, for these mutations, we did not have data to compare directly against delta Gs with the experimentally measured delta Gs. It's not available usually. What clinicians report usually are the restriction factors that are only related to the delta Gs. But we were able to establish a connection between the delta Gs and the restriction factors, and we built a very reliable classifier of those that are susceptible. So in the upper right quadrant, those would be correctly identified resistant mutations, resistance-inducing mutations, while those in the lower left quadrant would be correctly identified susceptible mutations, so those that actually even increase the binding affinity, or in this case restriction factor would be lowered for those mutations to a given drug. So we have a very good classifier, just which we extracted from the delta G values, and these were previously known mutations in affecting known ligands, but we also looked at new mutations. So in particular, L76V that I have marked here, this mutation is also known to either induce resistance or susceptibility, and our collaborators have acquired a number of new genotypes that this mutation acts on, or rather appears in. And we were also in almost all cases, just except of 2 outliers, we were able to correctly classify those effects. And once we were able to classify those effects, we could also identify the underlying cause, why this resistance or susceptibility occurs upon this mutation. And a particularly interesting thing is that once mutated away, this leucine 76 allows lysine and aspartate amino acids just to form a hydrogen bond, which changes the overall allosteric network, and which changes then the interactions of a particular ligand binding to the active site. So this mutation indirectly without acting directly on the ligand, it indirectly changes the binding affinity, and in turn the restriction factors, and induces the resistance or susceptibility to other ligands. Not only can we do this for the HIV protease, of course, my colleague Matteo Aldeghi, he looked into a large number of proteins that are binding various ligands that you can see in this figure. So in total 17 systems with 27 different ligands bound, and he looked at more than 100 mutations in those in all of those proteins to check how accurately can these drug resistant mutations be predicted. And in this case again we see that the consensus approach between Amber 14 force field and Charm 22 star gives an agreement with the experiment which is lower, which reaches about 1.2 kilocalories per mole of difference from the experimentally measured free energy differences. So this would be it for the free energies for the amino acid mutations. I have one more application that I would like to talk about. It is amino acid mutations in the protein-protein binding process. However, for this particular topic, I would like to go into a bit more detail in the short talk that is scheduled for the afternoon. And currently, I would like to already switch to the DNA nucleic acid mutations. So, in this case, we will be mutating DNA and looking at the thermodynamic cycles like as visualized here. I will come back to this in a few minutes. Now, the underlying mechanism, how we will be doing this, is very similar. So we will again be using PMX. Just in this case, as previously we used amino acids to create hybrid structures and topologies, here we'll be using nucleic acids, nucleotides to make a hybrid nucleotide structure and topology. In this case, so all the technical details are identical to the amino acids, except that the library is also smaller and it contains different elements there, right? Also, we have a web server which can do the whole process automatically. Let's have a look at the application of protein DNA of these alchemical calculations and protein DNA binding. So the thermodynamic cycle is as follows. We are interested in mutating a nucleotide in a DNA which is in its unbound form. So in comparison, as a reference, we will use I'm sorry, this will be our reference free energy delta G1, and delta G4 will be our DNA, our DNA mutation of a molecule bound to the protein. And in total, this will give us a relative free energy difference of DNA binding to the protein upon a nucleotide mutation. To probe how accurately we can calculate these free energy differences, we looked at a very large number, so almost 400 mutations in 16 different protein DNA complexes. These complexes comprise transcription factors and nucleases. You can see in more detail here if you're interested. But right, so they are very, very diverse systems, right? And if we pull all of the data together, so from all of these systems, we can plot them experimental versus calculated free energy differences. We can see that we get accuracies that are that at most accurate predictions would reach in total average would reach 5.5 kilojoules per mole error from the experiment. this is slightly worse than the desired 1 kilocalories or 4 kilojoules per mole error that we saw for the amino acid mutations. However, of course, in this case, there are several things to note here. For example, that the experimental values, if we look at the plot on the left, they seem as if they have a very strict capping region. So this indicates that it's likely that experimental measurements themselves, they have a certain range where they could measure the changes in the affinity. However, of course, calculation does not have any limitation in that respect. So maybe it is also both inaccuracies in the experiment or a limitation of the measurement range from the experimental side, and also inaccuracies that we have from our calculations that contribute to this slightly larger error. And again, we probed amber, charm, and the consensus force field, and we see that if we have a consensus approach, we are outperforming any individual force field as taken separately. Now, where could we apply such a calculation of delta delta G for protein DNA binding? Well, we could construct something what is called a DNA profile, DNA binding profile. So this is a profile that is acquired from an experimental measurement, and it shows what frequency of a nucleotide you would find at a given DNA position. So what nucleotide would be preferred there. We could also recalculate such profiles from our calculated delta delta G values, and once we do that, we obtain, well, similar profiles. And now it's interesting to note that the top profile, the one on the top panel, is obtained from our calculations. However, the 4 lower profiles are obtained from different experimental techniques, and we can see that it is, and we can even quantify. I'm not going into the details here, but our computational profile is very much indistinguishable from the different computational techniques. So it could be considered to fall well within the experimental error of identification of these profiles. All right, with this we can proceed to our third part, to the ligand modifications, ligand free energy calculations. And here we will be looking at a slightly different approach, because the same strategy will not work anymore. So pre-building a library for canonical amino acids or nucleotide mutations will not work, because ligand modifications can be a set of them can be very diverse, and every ligand pair that we would consider would be unique, since the chemical space is nearly infinite. So what we do, we apply a different strategy. Here we build 3 different modules that would allow dealing with any arbitrary modification. For that, we would firstly need to identify atoms that would need to be morphed between the 2 considered ligands. To do that, we can either align the 2 molecules. If they're similar, then the mapping will be quite good. However, if they're not similar in their own 3D structure, we rely on the maximum common substructure, so on a graph-based comparison of the 2 molecules. This is all encoded in a rather complex workflow, but the user doesn't need to worry about this. Simply the algorithm will be probing one path, will be probing another path, and will be choosing a more suitable solution. For example, if we were to align these 2 molecules, we could identify either on the left maximum common substructure, which would be one solution. Alignment would yield a different solution, and then the algorithm would be intelligent enough to choose the better one according to its measures. Subsequently, we have an automated technique to build hybrid structures and topologies, and we also have suggestions for ligand pairs in a small network of compounds. For example, if we have a network of compounds, if we have a compound library that looks like this here, visualized. We would like to know which ligand would we like to mutate into which, so that we cover all this chemical library. So we build a pairwise matrix, so based on the distances that our algorithm calculates intrinsically, and devises a distance matrix. Subsequently, this distance matrix can be built into can be transformed into a minimum spanning tree, or several trees, so that we would have redundancies in the library. Now let's look how we could apply this this approach. So we have scanned a very large set of ligand modifications for ligands binding to a protein. So in a sense, we were acquiring delta G's in the following thermodynamic cycles, where we looked at the ligand modification in water, and also in the same ligand modification when the ligand is bound to the protein, thus giving us the free energy difference of ligand modification of ligand binding to the protein upon that modification. Now we scanned 11 systems and probed almost 500 ligand modifications, and here is the overall summary of the results. There is a comparison of different force fields, GAF, CGNFF, and our consensus, and on the left here we see also the FEP+, which is a different approach from a commercial software company, Schrödinger company, which is frequently used in the pharmaceutical industry. If we look now at the accuracies in terms, for example, let's look at the average unsigned error. The top panel there, we see that a consensus approach performs either as well or even outperforms the best results of the FEP+. And in the Pearson correlation, we are also well within the error bars of the best commercial software. And again, consensus approach performs better than any single force field considered separately. Now, the performance of calculations strongly depends on the system that is being explored. Here I have now broken down all these results by system. On the x-axis, there is in each of these plots, it's the experimental value, and on the y-axis is the calculated delta G value. We can see that the more red dots there are, the worse the prediction, the worse the calculation accuracy is. And we can see that some systems really perform really well, very the clouds look very blue there, so we have high accuracy, but it strongly depends on the system. Now we for the last 3 minutes of my talk, I would like to also tell about the absolute free energy calculations, because not only can we do the relative free energy calculations, we can also look at the disappearing or appearing the ligand, full ligand. In this case, we would not get a delta G, but we would really aim to compute the absolute delta G value. This would, however, require a slightly different protocol. We would require restraints. So the ligand, when it's decoupled, there on the right side, it would need to be restrained somehow to the protein, and those restraints would need to be taken into account in the free energy estimation. The perturbations are, of course, larger in this case, and hence the convergence will be slower. The protocol here can be visualized also as this thermodynamic cycle. We want to disappear the ligand, so decouple it from solvent on the left side, apply the restraints, and recouple it when it's bound to the protein, and also remove the restraints. So the cycle is slightly more complex than those cycles that I was showing before. Now, as a test how well our approaches work, we can use a test system which has been recorded, which has been collected by Aldeghi and the colleagues. So in 2017, so several years ago, Matteo collected a set of 22 bromodomain proteins. Those are proteins that interact strongly with the bromosporin, which is a ligand inhibiting those bromodomains. And there is also experimental data available on the absolute binding free energies of bromosporin to all of these bromodomains. And what Matteo did then in 2017, he calculated, he used the Hamiltonian replica exchange enhanced free energy perturbation technique, so equilibrium technique, and obtained the results that are visualized in the upper left panel. Now we wanted to see what would happen if we were to apply either not apply this enhanced replica exchange protocol, just simple FEP. We see this in the middle panel, in the upper row, middle panel. We see that the accuracy drops. So from 1.5 in the average unsigned error, we drop to 2.3 average unsigned error. That's quite a large drop in kilocalories per mole. And what if we apply the non-equilibrium free energy protocol? Well, we gain in accuracy, and accuracy becomes almost identical to that which is achieved by Hamiltonian replica exchange FEP approach. In terms of Pearson correlation, we actually, with the non-equilibrium approach, can reach the highest accuracy of these three methods, almost reaching 0.6 in Pearson correlation. We can also look at the breakdown by system, but of each of these energy estimations. But maybe it's more interesting to look at the convergence. So we here in the panel C, I'm showing the convergence, or rather average unsigned error of all of these calculations depending on the sampling time used per obtaining a single delta G value. And we see that the non-equilibrium free energy protocol converges very quickly to its final accuracy, while the non-enhanced free energy perturbation protocol takes quite some time, and even after the 650 nanoseconds invested per single delta G calculation, it still has not converged to the enhanced sampling technique result. Alright, so with this I think I'm finished, and just to summarize, what we looked at today was alchemical free energy calculations of amino acid mutations, nucleotide mutations, and ligand modifications, as well as a little glimpse at the absolute ligand free energy calculations. Yeah, thank you. My acknowledgement slides, and thank you.